Good morning, everyone.
Good morning.
Good morning.
Good
How are
morning.
you today?
Good.
Tired, but I'll push through.
So, as you know, I divided the exam into two parts, each worth 50 points. And the first part will be during the class. It will not that much big. It will be during the exam from 4 to 5:15 p.m. But the second part will be during the 24 hours. So you can answer the second part at any time. The first part will cover unit 6, 7, 8, and the second part will cover unit 9 and 10. So the first three parts, first three units, uh, I give the questions like similar to the homework, like calculations, interpretation, short answer, and these kind of things. So if you are not going to do anything by R during the class, but the second part will be R, mainly will be R. Like I will give you some data set and you analyze this data set or you answer some questions about this data set. For sure, I will give you some data set to compare two population means or comparing two population proportion because the other two units, 9 and 10, cover two population proportion, two population means. So I'll give you a data set and ask you some question about this data set. So the answer, to answer the question, you need to run R. And there are two files uploaded on Canvas, R, one for two population proportion and one for two population means. So you need to modify these ones a little bit to answer the question. So either the part one or part two shouldn't take much time. I do this one to decrease the stress of exams. I know exams are stressful. So I try my best to help you. Okay. Any questions? Any questions?
I was wondering if the in-class exam had like if you would give us questions with like R output and then we would need to interpret the R output, or if it would just strictly be like short answer, like in theoretical interpretation type of questions.
It will be both types of questions. Like I gave you some questions about short answer, some questions about I give you R and you and to interpret some of the outputs in R or use the output to calculate something. If I gave you some data set, it should be a very small data set, so you can calculate what I'm asking for. So you can calculate the average, you can calculate the standard deviation or variance, but it's a small data set, so you can calculate this one very quick.
Okay.
But if something need to be done with R, I will do it by R and give you the R output, and then I'll ask about the output, something like interpret something or calculate something from the output and so on. Does it
Okay.
answer your question?
Yeah, thank you.
You're welcome. Any other questions? Okay, so today I'm planning to go over unit 6, 7, 8, and 9, 10 will be on the second part. So let me go over these units. Let me set up my computer. And if you have any question at any time, please let me know. Just unmute yourself and ask your question. Mhm.
I just want to be clear for the take-home portion. We're allowed to start that whenever, right? Like I could work on
Yeah,
it
you can
like
start at
tomorrow at
any time. I'll
midnight.
give you 24 hours.
Okay.
I will release it at midnight, and you need to submit it by the next midnight. I'll give you
Okay, awesome.
24 hours.
Thank you.
You're welcome. Any other questions? Okay. Okay, I will go over unit 6, 7, 8. Unit 6 about estimation and inference for a population mean mu when sigma square is known. So unit 6 is populate estimation and inference about a population mean. Assuming the population variance is known, which is sigma square. So unit 6, estimation and inference about a population mean mu, assuming you know sigma square. Unit 7 is estimation and inference about a population variance sigma square, assuming the mean is mu is known. Unit 8 is estimation and inference for the two parameters, mu and sigma square. This is the reality because of both are unknown all the times. So, but we assume one of them is one of them is known to make the problem simple, and there is a very rare situations that have these kind of applications. So, unit 6, the idea is I select a random sample. Let's say y1, y2, up to yn. And I want to make estimation and inference about the population mean of the population mean that I selected the sample from, assuming sigma is known and mu is unknown. So let's assume we selected a random sample of y1 up to yn from a population its mean mu is unknown and its variance sigma square is known. So the one we are interested in unit 6 is the mean mu. So how do I make estimation and inference about the population mean mu? There are two approaches, frequency approach and Bayesian approach. The frequency approach use only the likelihood, and Bayesian approach use the multiplication of the likelihood by the prior distribution. So the maximum likelihood estimation is one of the methods in the frequency approach. There are many methods for estimation and inference in frequency approach. One of them is the very famous one is maximum likelihood. The maximum likelihood uses only the likelihood. So how do I get the likelihood? You need to assign a data distribution first. The y follows what distribution? We assume the follows normal distribution. So if they follow normal distribution, what is the joint probability mass function? The probability of y1, y2, up to yn, given we know mu, given we know sigma square. So you assume a distribution for the data first, and if you'd like to calculate probabilities, you assume mu and sigma square is known. But if you'd like to do inference and estimation of about the parameter, you need to collect data, so y's are known and the parameters are unknown. The probability mass function is the multiplication of the density function of each value, like y1 follows normal distribution, assuming y1 is randomly selected from normal distribution with mean mu and variance sigma square. So the function will be 1 divided by 2 pi square root sigma e to the power negative half sigma square y1 minus mu square. The second one is randomly selected from normal distribution. Third one, normal distribution to the last one. Randomly selected from normal distribution with mean mu. So square root of 2 pi sigma and variance sigma square. So 1 divided by 2 sigma square yn minus mu square. When you multiply these together, you get 1 divided by 2 by sigma square all to the power n over 2 e to the power negative 1 divided by sigma square sum over I equal 1 up to n yi minus mu square. This one is the probability, the joint probability function of y1 up to yn. If this one assumes mu and sigma square are known, but if if mu is known and mu is unknown and sigma square is known, we can and we selected the data y1 up to yn and plug in these values in this equation. The only thing is unknown as mu. So the likelihood of mu, given that we collected the data vector of values and sigma square is known, in this case, this one equal 1 divided by 2 by sigma square all to the power n over 2 e to the power negative 1 divided by 2 sigma square sum over I from 1 to n yi minus mu. So maybe you ask me, it is the same thing. Yeah, I know it is the same thing, but the difference is this one, we assume y's are unknown and mu and sigma square is known. In this one, we assume mu is unknown and the data is known. We collected the data and we assume sigma square also is known. So I can remove anything is not a function of mu. And I write it down as its likelihood proportional to remove anything doesn't have mu. So this one doesn't have mu. So e to the power 1 divided by 2 sigma square sum over I equal 1 up to n yi minus mu square. This one is the likelihood. So in the frequency approach, follow some steps to get the estimation of mu head. You take the natural log of this likelihood and then take the derivative with respect to the parameter mu and then set equal 0 and solve for the equation. You will find mu hat, which is y bar is the sum of yi divided by n, which we called it sample mean. So this is the estimation for the frequency approach. It uses only the likelihood, but Bayesian approach is different. Bayesian approach, we multiply this likelihood by something called the Brier distribution of mu. So what is a Brier distribution? This is a distribution that we add our beliefs or previous study or something else into the estimation and inference. So the second approach is Bayesian approach. In Bayesian approach, we find something called the posterior distribution of mu given the data and sigma square. Sorry, guys. This posterior distribution of mu that has all the information we have proportional to the multiplication of likelihood of mu given we know the data and sigma square times the Brier distribution of mu. So we know the likelihood that frequency approach uses. What about the Brier distribution? The Brier distribution is a distribution that you can add your information in, and that will add a source of information to the estimation and inference. So how do I get this the Brier distribution of mu? There are many ways, and we cover two. The first one is Jeffreys Brier. The second one is conjugate Brier. From unit 1 up to unit 5, you are familiar with what do we mean by conjugate Brier. Is a Brier that if I multiply this Brier by the likelihood, I get a posterior distribution from the same family. And what is the Jeffreys Brier? This is a non-informative Brier. They call it reference Brier, so you can compare your analysis with the analysis that has Jeffreys Brier. Jeffreys Brier is a non-informative Brier, and use this one when you do not have any information about the population mean. Sometimes you have some information, or there is some previous study, or you have some beliefs about the population proportion, but sometimes you do not have anything, so you can use Jeffreys prior as the probability of mu proportional to 1. So something like you multiply the likelihood by 1. And we showed that in class that this prior distribution actually is equivalent to normal, 0, and infinity. So this Jeffreys prior is actually normal, 0, infinity. So you can use this prior distribution, but actually we do not use 0 infinity. We use something like normal, 0, and 100 or 1000. This one is enough. So you can use this prior distribution as a non-informative prior. What about the conjugate prior? The conjugate prior is normal distribution, because when we looked at this likelihood, we found it is a kernel of normal distribution. This one is a kernel of normal distribution with mean y bar and variance sigma squared divided by n, or in terms of tau's precision is 1 divided by n tau squared. So this is why we decided to work with normal distribution as a conjugate prior, with some mean mu 0 and some variance 0 sigma squared, 0 squared. So how do I find mu 0 and sigma squared? I will talk about this one because this is very important. How do I find mu 0 and sigma 0 squared using previous study or based on my beliefs? It is very simple. There are many ways to get mu 0 and mu 1. One of them is you can find previous study. You can use previous study. How do I use previous study to find mu 0 and sigma 0 square? The mu 0 is the mean of y. The previous study, they collected data about the response variable y. So calculate the mean of y. It will give you mu 0, and sigma 0 square is the variance of y. Take the variance of the previous data. So now you plug in mu 0, plug in sigma 0 square, done. You get these two. Or you can use the idea of equivalent sample size. The idea of equivalent sample size. How do I use the idea of equivalent sample size to get this normal mu 0 and sigma 0 square? So the idea is selecting mu 0 is not that much hard. Like I feel like the population mean is something like 25. So you select this one by yourself. But the problem is this one, sigma 0 square. What is the variability? This one represents how much certainty you have about the population mean mu 0. If you do not have much, if you do not feel confident, you use sigma 0 square, a big value. If you feel confident, use sigma 0 square as a small value. But the idea of equivalent sample size is what? The idea is I feel confident with mu 0 that I selected equivalent to the confident in the sample size of sample of size 0. What do you mean? I mean, I would like to have a prior distribution that has information about the population mean mu equivalent to the information in a sample of size n0, some sample size. If the sample size is big, you have more information, you are more confident, you have more certainty about mu 0. If the sample is small, you do not have much info, you do not feel confident, or you do not have much, like equivalent to, you do not have much information about the population parameter. So selecting mu 0 is easy, but selecting sigma 0 square is not easy. So use the formula that n0 equal tau 0 square divided by tau square, which is sigma square divided by sigma 0 square. So assume this one is known, and you as a researcher, you select this one, something like I wanna have the information in the prior distribution of mu equivalent to the information in a sample of size 100. So this one is 100. And this one is known, let's say this one is 2, for example. Divide by sigma 0 square. So now we can find sigma 0 square. It is 2 divided by 100. It is 0.02. So this is how to find sigma 0 square using the equivalent sample size idea or method. But there are many other methods, like you can graph many normal distributions and see which one match your belief. Or you can graph many ones with 95% confidence interval and see which one match your belief, 95% credible set. And see which one match your belief and so on. There are many ways, but the very famous ones are previous study or equivalent sample size or the one match your belief. So now if I selected mu 0 and sigma 0 square and I have the likelihood, I multiply these two together to get the posterior distribution. So you get the posterior distribution of mu given y and sigma square as proportional to the likelihood of mu given y and sigma square times the probability of mu. When you multiply these together, you get the posterior distribution. And let's use normal distribution in general for the prior distribution because we found the Jeffreys prior is normal and the conjugate prior is normal. So let's find the posterior distribution in general when we use normal distribution. And if you use Jeffreys prior, just plug in mu 0 equal 0 and sigma 0 square equal infinity. So when you multiply these together, assuming this one is normal, mu 0 and sigma 0 square, and this is likelihood, you will find the posterior distribution of mu given y and sigma square is normal distribution because you used a conjugate prior. The posterior will be normal with mean n y bar tau square plus mu 0 tau 0 square divided by n tau square plus tau 0 square. This is the mean or the posterior mean or the estimation of the population mean mu with variance 1 divided by 2 tau square plus tau 0 square. Tau square is 1 divided by sigma square, which is known, so tau square is known. Tau 0 square is 1 divided by sigma 0 square, and you select 0, sigma 0 square as a researcher, so tau 0 square is known after you select the sigma 0 square. This one is called the posterior mean, and this is the estimation of mu. And also this one equals the posterior median because this is normal. So the mean, median, mode, they are equivalent. And also the posterior mode. So these three ones are equal and it's very simple. So after you calculate, you plug in n, y bar, tau squared, mu 0, tau 0 square, you get the posterior mean. This is the estimation of mu using Bayesian approach. And this one is the posterior variance of the parameter. So it is very easy in terms of we do not have many formulas like posterior mean is what, posterior median is, posterior mode is what. It is only one formula, which is this one. But this one under conjugate prior, normal mu 0 and sigma 0 square. This is the posterior distribution under conjugate prior, normal mu 0 and sigma 0 square. What about under Jeffreys prior? Jeffreys prior is also normal distribution with mean 0 and infinity. Infinity means this infinity is sigma square. Infinity is sigma square, sigma 0 square. So when you calculate tau 0 square, it will be 1 divided by infinity, it will be 0. So you look at this formula and plug in tau 0 square is 0. When you plug in tau 0 square is 0, it gives me the posterior distribution of mu given y and sigma square is normal again, whereas this tau 0 square is 0, tau 0 square is 0, so and then you will find ny bar tau square divided by n tau square, it gives me y bar. And when you plug in tau 0 square in the second one, this one is n. Why I wrote it as 2? Guys, if I do any mistake, let me know. When you plug in tau 0 square is 0, it gives you 1 divided by n tau square. It will give me sigma square divided by 2, or write it down in terms of taus, it will be y 1 divided by n tau square, which is sigma square divided by n. So this one is the posterior distribution under Jeffreys prior, the posterior distribution under conjugate prior for the population mean mu. And you use this one for estimation and inference. So you can graph this function. You can graph this function. So now if you'd like to do anything, estimation or inference or anything, use this posterior distribution. You can graph the function by R. You cannot do by hand. You can calculate credible set by R using the Q-norm function. You can calculate the probability of H0. You can calculate the probability of H1 using the R function. The R function is P-norm. You can divide probability of H1 by probability of H0, you get the posterior odds. You can calculate the probability of this one should be probability of H0 given Y. The probability of H1 given Y. Because we calculate the probability after collecting data. You can calculate the posterior odds by dividing probability of H1 given Y divided by probability of H0 given Y. Or you can calculate the posterior, the prior odds by calculating the probability of H0 only, probability of H1 only, without the data. So you use the prior distribution only, normal 0, sigma 0 square, to calculate probability of H1, probability of H0, and you divide these two, you get the prior odds. And then you can divide the posterior odds by the prior odds, you get something called Bayes factor. But all of these ones by R. So you have the posterior function, but you cannot do anything by hand. You can graph the function by R, credible set by R, the prior odds, posterior odds, and calculate the probability of H0 given Y, probability of H1 given Y, all these ones by R. So this is unit 6. Do you have any questions about unit 6? Okay. If there is no question, so let's go to unit 7. Unit 7 is population and inference. Estimation and inference. Estimation and inference about a population variance sigma square, assuming mu is known. So the idea of this chapter is, the idea of this unit is, let's select a random sample from some population. Select a random sample from a population. Its mean is known and the variance is unknown. There are some applications in these two cases, Unit 6 and Unit 7, but it's not much. But in this case, we work with only one parameter to practice on one parameter many times, and then we practice on 2 parameters, 3 parameters, and any number of parameters. So how do we do estimation and inference in this case? The sample you selected is from Y1 up to Yn. You have this random sample, randomly selected from a population. Its mean is known, its mean is mu is known, and its variance is unknown, sigma square. So you need to do estimation and inference for the unknown value, sigma square. The frequency approach use the likelihood. How do I get the likelihood? You get the likelihood from the data distribution, as we have done before. So this is the data distribution. This is the data distribution, this one. So let's write it down again. The data distribution for the joint probability mass function Y1 up to Yn, given you know mu, you know sigma. This one is 1 divided by 2 pi sigma square, all to the power n divided by 2, e to the power negative 1 divided by 2 sigma square, yi minus mu square, and take the sum over I equal 1 up to n. So the likelihood of sigma square, given the others are known, sigma square, given mu is known, y1 up to yn, or a vector of y known, this one is 1 divided by 2 pi sigma square, all divided by n over 2, e to the power negative 1 divided by 2 sigma square, sum over I from 1 to n, yi minus mu square. So it is the same. Yeah, I know it is the same. It depends on which one is known, which one is unknown. So now if you'd like to simplify this one, so L of sigma square given mu and the vector of y is proportional to, remove anything is not a function of sigma square. The only thing is not a function of sigma square is this part. So it is 1 divided by sigma square all to the power n over 2, e to the power negative 1 divided by 2 sigma square, sum over I equal 1 up to n yi minus mu square. So the maximum likelihood estimation, use this likelihood, the frequency approach, use this likelihood to find the maximum likelihood estimation. The maximum likelihood estimation after taking the natural log of this function and then take the derivative with respect to sigma square and then equal to 0 and then solve, you will find sigma square hat is the sum of yi minus mu square divided by n. Assuming mu is known, this is the maximum likelihood estimation of sigma square. But in Bayesian approach, we do not use only the likelihood, we use the likelihood multiplied by the prior distribution. So the Bayesian approach get the posterior distribution of sigma square, given we know y's and we know mu. This one proportional to the likelihood of sigma square given y and mu times the prior distribution of sigma square. So now, as we have done with the population mean, how do I find the prior distribution of sigma square? We cover many situations. You can use non-informative prior, Jeffreys prior. This one is the probability of sigma square proportional to 1 divided by sigma square. You can use conjugate prior. The conjugate prior is inverse gamma with alpha and beta parameters. And we found that Jeffreys prior also inverse gamma with alpha 0, beta 0. But the problem with this one, it is this prior is improper prior because there is some condition on alpha and beta. If you looked at the distribution table on Canvas, you'll find alpha should be greater than 0, beta should be greater than 0, not equal 0. So this one is improper prior. So this one, they said, okay, no problem. We can use inverse gamma with very small value for alpha, very small value for beta. So you can use inverse gamma 0.1, 0.1, or inverse gamma 0.01, 0.01. These ones are non-informative, but at the same time they are proper priors. So looks like whatever we are using, Jeffreys prior or conjugate prior or any other prior, it is inverse gamma. So you multiply inverse gamma by the likelihood, and you will find the posterior distribution is also inverse gamma. So let's multiply these together and get the posterior distribution. After you multiply the inverse gamma by the likelihood, you will find that the posterior distribution of sigma square given mu and y, it is also inverse gamma with two parameters, alpha plus n over 2 and beta plus n s squared divided by 2. What is s squared? It is the sum of yi minus mu squared divided by n, assuming we know mu. So you can call this one alpha, new beta, or alpha star, beta star. It's up to you. So let's call this one is alpha star, this one is beta star. So now if I would like to estimate the population variance sigma square by the posterior mean, there is a formula. The posterior variance, there is a formula. Posterior mode, there is a formula. Posterior median, there is a formula. So mean, mode, median, those are the three methods for estimating sigma square. So sigma square hat equal based on Bayesian approach. But this one represents the variability. And this one has some formula also. So you can have these formulas in the formula sheet or any other formula you may need. You can write it down in a formula sheet, the formula sheet. So this is how to estimate the population variance sigma square. But we haven't talked about the idea of how do I select alpha and beta as we have done with mu 0 and sigma 0 square. There are many ways also. You can graph many plots or graph many inverse gamma and see which one match your belief by R. Or you can select using previous study. So how do I use a previous study to find alpha and find beta of the prior distribution? Using previous study, it is the alpha is the sample size of the previous study divided by 2 minus 1. And beta is the sample size of the previous study times the variance of the previous study divided by 2. You can call it S square or call it sigma 0 square, the variability of the previous data. This is how to find alpha and beta for the prior distribution. Or you can graph many functions, many inverse gamma, and see which one match your belief, and so on. So there are many ways. Or you can graph 95% credible set for many ones and see which one match your belief, and so on. What if I use Jeffreys prior? If I use Jeffreys prior, it will be again inverse gamma, but plug in alpha equals 0, beta equals 0. Because under Jeffreys prior, which is inverse gamma, 0, 0. If you plug in alpha equals 0, this one is alpha, this one is beta. So you will find the posterior distribution is inverse gamma again. Plug in alpha equals 0, so alpha star will be n divided by 2. Plug in beta equals 0, it will be ns squared divided by 2. This one is the posterior distribution. When you use Jeffreys prior for the population variance sigma square. So, and again, as we have done before, if you'd like to calculate if you'd like to do some inference, like you get credible set by R, use inverse gamma function, Q inverse. If you'd like to get the probability of H1 given Y, probability of H0 given Y, you can use R function, which is P inverse gamma. And then you divide probability of H1 given Y by H0 given Y, you get the posterior odds. And also you can use R function to get the probability of H1 and probability of H0 before collecting data using only the Breyer distribution. And then you divide these two, you get something called Breyer odds. And then you divide Breyer odds, posterior odds by Breyer odds, you get something called Bayes factor. So this is how to do estimation and inference for a population variance, assuming the population mean is known. This is unit 7. And then we go to unit 8. But before I go to unit 8, any questions so far? Any questions so far? Okay, let's go to unit 8. In unit 8, we assume mu and sigma square are unknown. So unit 8, estimation and inference. For mu and sigma square, assuming both are unknown. So in this case, we select a random sample from a population. Its mean mu is unknown and its variance sigma square is unknown. This sample is y1 up to yn again. So how do I use this sample to do estimation and inference using frequency approach and using Bayesian approach? In frequency approach, we use the data distribution, the likelihood, and from the data distribution, and in Bayesian approach, you multiply the likelihood by the Breyer distribution about mu and Breyer distribution about sigma square. So in this case, using frequency approach, it use the likelihood. And the likelihood, as we have done before, this one, this likelihood. It is the same again, but in this case, we assume, the likelihood is, this is the data distribution, and the likelihood is this one, but assume both are unknown. So let me write down the likelihood. The likelihood L of mu and sigma square are unknown, given the only thing is known is data. This one equal 1 divided by 2 by sigma square all to the power n over 2 e to the power 1 divided by 2 sigma square sum over I up to n, I equal 1 up to n mu square. So in this case, I will remove only 1 divided by pi. So the likelihood is mu and sigma square given y proportional to 1 divided by sigma square all divided by n over 2 e to the power 1 divided by 2 sigma square sum over I equal 1 up to n yi minus mu square. This is the likelihood of both parameters. And how do I get the frequency approach estimation for mu and sigma square? You take the natural log, take the derivative with respect to mu, takes the derivative with respect to sigma square, and then pose equal 0, and then solve for mu, solve for sigma square. You will find the estimation of mu is y bar again, sum of yi divided by n, and you found the estimation of sigma square based on the frequency approach, producing the maximum likelihood estimation is the sum of yi minus y bar squared divided by n. So we replaced mu by y bar because also y bar is unknown. So this is the estimation using frequency approach. What about Bayesian approach? In Bayesian approach, we multiply the likelihood by the prior distribution to get something called posterior distribution. This is the probability of mu and sigma square given we know the data. This one equal or proportional to the likelihood of mu and sigma square given we know the data times the prior distribution of mu and sigma square. If they are independent, so this one is the proportional to mu sigma square given y times the prior distribution of mu times the prior distribution of sigma square. So what is the prior distribution of mu? Can be normal, mu 0, sigma 0 square. Prior distribution of sigma square can be inverse gamma with alpha and beta. So now let's multiply these three and then get the posterior distribution of sigma square, posterior distribution of mu. The problem here is you cannot do it, or it is not easy to do it. Because if you'd like to get the posterior distribution of mu, you take the integral over the whole range of sigma square of the multiplication. So to get rid of sigma square, and you get the posterior distribution of mu given the data. And if you'd like to get the posterior distribution of sigma square, you take the integral over the whole range of mu to get rid of mu, and you get the posterior distribution of sigma square given me data. So this one is not easy. I know in this case I cannot do it, but you will hate me if I showed you how to get the posterior distribution of mu and sigma square. So we need to learn what is the situation if we are not able to do it. The solution is you get the conditional distribution of mu and the conditional distribution of sigma square. It means get the distribution of mu that depends on sigma square, or assuming sigma square is known, and get the distribution of sigma square assuming sigma square is known. In this case, you will find the posterior distribution of mu, or the conditional distribution of mu given sigma square and y is normal distribution with mean y n y bar tau square, which is 1 divided by sigma square, plus mu 0 tau 0 square, which is mu 0 divided by sigma 0 square, all divided by, if you remember, 1 divided by, if you remember, it is n tau square, so it is n divided by sigma square plus tau 0 square, which is 1 divided by sigma 0 square. And the variance is 1 divided by n tau square, which is n divided by sigma square, plus tau 0 square, which is 1 divided by sigma 0 square. I write it down in terms of sigma 0 square and sigma square to see that the posterior, the distribution of mu depends on sigma square. So this is why we call this one conditional distribution of mu given sigma square. And the conditional distribution of sigma square given mu is known and y is known is normal distribution with with inverse gamma distribution with alpha star alpha 0 plus n over 2, or you can call it alpha plus n over 2. It's up to you. So assuming the prior distribution is inverse gamma with alpha 0 beta 0, you can use alpha 0 beta 0 or alpha and beta. It's up to you. And the second parameter, alpha beta star, is beta 0 plus 1 divided by 2 sum of yi minus mu square. But before you used n s squared divided by 2, I know. But I change it n s squared to be sum of yi minus mu, because I want to show you that the distribution of sigma squared depends on mu. So now we have two conditional distribution. This is conditional distribution of sigma squared given mu. When you look at the first one, the conditional distribution of mu, it depends on sigma squared. When you look at the conditional distribution of sigma squared, it depends on mu, the formula itself. So what should I do? Each parameter depends on the other. So the idea is use Gibbs sampler. What do you mean? I mean, let's select initial values for mu, let's call it mu 0. And for sigma square, let's call it sigma square 0. You plug in this one in this one. And then you randomly select one of sigma squares, one value from the distribution of sigma square. And you plug in this one in this one. And you select randomly one value from the distribution of mu. So now we have one more mu and I have one more sigma square. Let's call it 1, 1. And then you do it many times, like 10,000s of times, or 1 million of times, or 10 millions of times. So now you have a random sample, or a sample from. So these two samples are randomly selected from the conditional distributions or the marginal posterior distribution. There are some proofs and theorems. They said after some a few values, if you ignore these values will be random samples from the marginal posterior distribution of mu given the data, not given sigma square and data. So this one will be considered a random sample from the posterior distribution of mu given only data, doesn't depend on sigma square. And this one will be a random sample from the posterior distribution of sigma square given the data, not given mu. So something like after some number of iterations, the values we randomly selected from the conditional distribution doesn't depend on the other parameters. So now if I have a random sample from the posterior distribution of mu, a random sample from the posterior distribution of sigma square, I can do whatever I want. You don't need to give me the function of probability of mu given y and the function of probability of sigma square given y. You give me random samples from these functions or these distributions or these posterior distribution. Now, if I would like to estimate mu, I will use the mean of these data. If I'd like to estimate mu by median, I'll use the median of these data. If I'd like to estimate the mean by the mode, I get the mode of these data. If I'd like to calculate the standard deviation, posterior standard deviation, I calculate the standard deviation of these data, and so on. If I'd like to get the credible set, 95% credible set, I will get the lower limit and upper limit of these data that is in between 95%. If I would like to calculate the probability of H1 given y, the probability of H0 given y, about the having this H0 and H1 about the parameter mu, I will use these data. If I would like to calculate the posterior odds, I will divide the probability of H1 given y times the probability of H0 given y. If I'd like to calculate the prior odds, I will use the prior distribution only to find the two probabilities, probability of H0, probability of H1, and divide. I'd like to calculate the Bayes factor. I divide the posterior odds by the prior odds. See, we don't need the marginal posterior distribution We need only the conditional distributions and use Gibbs samplers to give me a random sample from the marginal posterior distribution. And I do the same thing for the other parameter using these random sample. So the idea is when you have many parameters, sometimes you will not be able to find the marginal posterior distribution of each parameter. So you can use it to graph the function, use the R code to calculate, and these kind of things. So the only thing you can do, you can find is the conditional distribution. So how do I use the conditional distribution to do inference and estimation for the parameters? You use Gibbs sampler. But there are still some questions we need to answer. Like when we should stop, how many we should remove, how many initial values or how many iteration or the values from after what iteration I should remove. Or in another way, that when I should believe that the sample randomly selected from a posterior distribution. This one is called when the convergence happens. Convergence means the values I'm generating are generated from the true marginal posterior distribution. So when this one happens, when the convergence happens, there are many ways to make sure that the convergence happens or not. So let me go over these ones, the convergence. You can check convergence using the trace plot, because you can generate many parallel chains at the same time for each distribution. And if you see from the trace plot, the mixed well, it means the convergence happened. Or you can use Gilman-Robin statistic. If this one is close to 1, it means convergence happened, like 1.01, 1.05, or 1.1, or 1.2 is something, but it's not 1.5 or 2 or so. Or you can look at the standard error. The standard error should be less than the standard deviation divided by 20. Or you can look at the effective sample size. If the effective sample size of the parameter mu and the effective sample size of the parameter sigma square is a few thousands, so you can depend on these samples in estimation and inference. But if you found the effective sample is only 50, 70, 100, 200, is not big enough. So you need to keep running the iterations, keep running the algorithm until you get a bigger effective sample size. Or you can look at the autocorrelation. Plots. If the autocorrelation plots, like the lag 0 is always 1. And then you find the lag 1 is smaller, it means the samples you selected are random, and you will find the effective sample size is big. But if you see this situation, it means there is some dependency in the random sample, and you found the effective sample size is small. So if you see this situation, you need to run the algorithm many times, like 10 millions of times or something, to get a bigger effective sample size, so you can depend on it in estimation and inference. Yeah, guys, I feel like I'm done. If I missed something, please let me know. Do you have any questions? Any questions? Okay, I'm done with this one. So, this is unit 6 to unit 8, 6, 7, 8. That will be covered during the class. You can have a formula sheet, and I'm planning to have something like 4 questions, but each question has many parts. And I'm not going to ask you to do many things. calculation it will be simple, but most of the times it will be interpretation and short answer and these kind of things. And if I give you some data sets, it will be a small data set, so you can calculate the average very easily, you can calculate the variance very easily, and these kind of things. Okay, any question? Okay, thank you so much, and see you in class on Monday. Have a good day.
Thank you.
Thank you. Have a
Thank
good
you.
weekend.
You
Thank you.
too. Thank you.